Welcome to Brain Vision.
In this question, we are basically applying Bohr's model to a gravitational perspective, right? Rather than an electron orbiting around a nucleus, we have a satellite orbiting around our Earth. Let's see whether Bohr's model would work as well for this case. Well, the only difference is that instead of Coulomb interactions, we have gravitational forces acting as the main source of centripetal acceleration. So we start off this question using the Bohr's postulate, that is the angular momentum, mvr, is now an integer multiple of h over 2 pi. So n is an integer, right, element of the positive integers. We want to find what is n, which is equals to mvr times 2 pi divided by h by h. Now, a few things we do not have is the velocity. But we can convert velocity into period, right? Since velocity times the period must give us the circumference of the entire orbit. Therefore, the velocity is just 2 pi r over t. So we substitute that into here, we get 2 pi m times 2 pi r over t times r over h. This gives us 4 pi square m r square over t times h. So we just have put all the values in. So the mass of the satellite is given to be 20 kg, and the radius of the orbit is 8.06 times 10 power 6. The period is given to be in terms of 2 hours, so to convert that 2 hours into seconds, and h is the Planck's constant. Right, therefore we should get the quantum number over here to be 1.08 times 10 power 46. For the next part, we want to show that Bohr's angular momentum and the Newton's gravitational law, right, is directly proportional to the square of the quantum number. Right, basically the radius is k times n squared. Now the way that we're going to do that is, well, we'll need to use the circular motion equation. That is, the acceleration, centripetal acceleration is v squared over r. This is equals to the gravitational acceleration, right, due to gravity. So this g times me over r squared. Therefore, v squared is gme over r. Now, since we have from our previous answer that right, from actually over here, we can simplify this a bit. V is equals to nh over 2 pi m times r. Sorry, this is a v square, right? So nh over 2 pi m times r square is equals to gme over r. So what we want now is to rearrange this equation to get r as the subject of this expression. So we multiply the r square from the left in here to the right side. Right, and therefore our r expression just n square times h square divided by pi square m square g m e. You can see that this is just all constants, right, which we can replace with just a simple k, right, where k, if you have to evaluate this, substituting all the constants in, is mass of the earth, we should get our k to be 7 times 10 to the power of minus 86. Now to find a distance between the allowed orbits in the satellite problem, basically we know that since the orbits can only go from n to n plus 1, so on and so forth in integer steps, right, we want to find what is the difference between each orbit, right, the change in the radii. What we want to do is to take k times n square, n plus 1 square, minus away k times n square. Right, so this is just adjacent orbits, right, from n to n plus 1. What is the difference in the radii? This just goes to k times 2n plus 1. Substitute in k over here, and our n value is already found in our first step. Right, this is our n value, 1.08 times 10 power 46. We should get something like 1.5 times 10 power minus 39 meters. Now this is a exceedingly small value, right? It is even smaller than the Planck's length, right, or even the Planck's constant, and therefore it is not an observable size, right? So even the size of an atom is about 10 to the power minus 15, right? The nucleus is about this size. It's way smaller than size of a nucleus. Therefore, this is really not observable, right, if the satellite were to jump between different orbits. Now, of course, there is no correct method. Basically, both methods are accurate and acceptable, right, for these calculations, because we are looking at a very large object. However, if you were to go to quantum level, where the classical way of measurement would not hold, right? So the classical way of continuity, continuous orbits would not be allowed, right, in the quantum world. But in a case when we are talking about such large objects, using a quantum picture would not affect the final calculations.